Hello grade 11s. Okay, so the first chapter that I want us to take a look at then is Intermolecular Forces under our chemistry. It builds on the previous chapter that we did about covalent bonding. So in the previous chapter we learned about what keeps atoms bonded to each other to form molecules. In this chapter we want to know, okay, we've got different molecules, but how can these molecules be bonded together to form liquids and solids and so forth? Okay, so here we're going to take a look at what we call the intermolecular forces, and then at the end of the chapter we're going to take a look at the chemistry of water, what makes water so important. We are going to split this up into different videos just to make them smaller and make it easier for you to view them. So before we start with anything then, we have to ask ourselves, why does matter exist as solids and liquids? Okay, and in grade 10 you guys learned about the kinetic molecular theory, where you learned that when matter exists as a solid or a liquid, they're held together by these forces. Now we are learning about those forces now, and those forces are what we call our intermolecular forces. Now what are interatomic forces? So inter meaning between, atomic meaning atoms, and when we again look on this side at the little molecule, we can go and see that that force there would be a interatomic force. Okay, intermolecular forces then is inter between molecular molecules, so that would be this force here, and that would be our intermolecular force. Okay, what is the relationship then between interatomic and intermolecular? We are going to take a look at that much later on. And we're also going to talk a lot about how covalent bonding plays a role in these types of bonds. Okay. Excuse me. So we can define intermolecular forces by saying they're forces that act between molecules, and it's going to be incredibly important for us to be able to define if a molecule is polar or non-polar. Okay, and from previous work you can remember that when we took a look at polarity, and if I use an example here, let's say for instance let's use hydrochloric acid, hydrogen with one valence electron, chlorine with 1, 2, 3, 4, 5, 6, 7, and if we then go look at their electronegativities, we can see that from the periodic table the electronegativity of hydrogen is 2.1. The electronegativity of chlorine is 3. So that means that this bond here, this shared electron bond, this covalent bond that formed, tells us that the difference in electronegativity between these two is equal to the larger one, 3, minus the smaller one, 2.1, which gives us 0.9. That means that this is a polar covalent bond. Okay, so now we know that it's a polar covalent bond. Then also from previous work we know that we learned how to show a dipole moment with this little arrow, and we said the reason we use it is because if we look at that part it indicates to us that slightly positive, and if we look at this part it indicates to us that slightly negative part. So it shows us our partial charges. Okay, so if we then look at our hydrochloric acid, that means that in this case the shared electron pair spends a little bit more time around the chlorine than it does around the hydrogen, making our dipole moment look like that. Meaning the chlorine side of the molecule is slightly negative, and the hydrogen side of the molecule is slightly positive. And remember what I told you, when we can draw a definite line through the molecule and find the opposite negative and positive side, we can then go and we can say that this molecule of ours is a polar molecule. Okay, so in this case what's important to understand is we said that it has a polar covalent bond, that bond there, and that the molecule itself is a polar molecule. Okay, if we go on to look at something like, let's say, carbon dioxide, no, before we get to those molecules, let's say a non-polar bond, non-polar molecule, or are diatomic molecules. So molecules that exist out of two of the same atoms, like let's say hydrogen gas, we can go and we can see here that we know the difference in electronegativity is going to be equal to 0, because it's going to be 2.1 minus 2.1. So that makes the bond, this little bond here, a non-polar covalent bond. Okay, then also the molecule itself we can go and we can say is a non-polar molecule. Okay, and that is the case for all diatomic substances. We can go a little bit further then, and we can take a look at what then about a molecule with polar covalent bonds, but the molecule itself is non-polar. And in this case we can take a look at something like carbon dioxide, where carbon has 4 valence electrons and it's bonded to 2 oxygens, and each one of the oxygens has got 6 valence electrons. Okay, so we know that the electronegativity of carbon is 2.5 and the electronegativity of oxygen is 3.5. That means in each one of these bonds, and remember we don't worry about the number of electrons in the number of bond, this is our bonded pair. So therefore the difference in electronegativity is equal to 3.5 minus 2.5, which gives us 1, making this a polar covalent bond. Okay, and because the 2 bonds are identical, both these bonds are polar covalent bonds. Okay, but the electronegativity of the oxygen is stronger than that of the carbon, meaning the shared electrons here are pulled towards the oxygen, making the oxygen slightly negative. And on the opposite side we have the same case where the shared electrons spend more time around the oxygen, making the oxygen slightly negative. Now the reason this is important is because there is no way we can draw a line through this molecule to find a definite opposite positive and negative side, and that means we say that this is a non-polar molecule. Okay, what's important here is the fact that this molecule has got polar covalent bonds, but it is a non-polar molecule. Okay, so it's very important for us to be able of still determining if it's a polar or a non-polar molecule. Okay. So, how are molecules polar? And that's exactly what we did now with those three examples. So I'm just going to go through it with you again quickly. So just because a bond is polar, that does not mean the molecule is polar. Like for instance the example we used with carbon dioxide. And very importantly, the shape of the molecule helps to determine the actual polarity, and that's where we learned about those ideal shapes in the previous chapter, and it is important that we take a look at them again. And I think the next video we will quickly just revise molecular shapes so that we do not get confused with those. So hydrogen diatomic, meaning non-polar covalent bonds, non-polar molecule. Okay, hydrogen chloride, we did in the example, polar covalent bonds, polar molecule. Carbon tetrafluoride, fluoride having an electronegativity of 4, carbon like we said in the previous one, 2.5. So the difference in electronegativity is equal to 4 minus 2.5, which gives us 1.5, and that makes this a very, very polar covalent bond. But the shared electrons in each case spend more time around the fluorines than they do around the carbon, making the entire outside of this molecule slightly negative, and it's got the general formula of AX4, which means that we are dealing with a tetrahedral molecule, so therefore ideal shape and a non-polar molecule. Okay, I'm going to stop here with this video. We'll continue with the molecular shapes in the next video.